Good afternoon, everyone. In the university, I have the love of the theoretical science. I'm Kurashige. Thank you very much for giving me this opportunity. In my lab, for the quantum chemical calculation, we are working for the research of algorithm, and this is the title of my presentation. The important point here is that when it comes to quantum computer, well, for the time being, we cannot use it in a universal way. So the quantum computer is used when it is necessary, and the classical computer can continue to be used in the general cases. So this hybrid would take place. So just separating those two is not sufficient. We have to connect each other. But it hasn't been discussed much, so I would like to focus on that point. So this is an introduction of my lab. This lab is not that big, but I have talented researchers. So the theme of the research is quite diversified. Up until here, it's a classical computer is used. For example, high development of high precision wave function theory, or designing of the metal complex catalytic capability. This is really chemistry. And we work for the photo energy materials as well as molecular spintronics. And one of those is this development of algorithm, quantum algorithm. Myself is the main researcher on this within my lab as well. Before getting into the technical part, let me introduce you the positioning of theoretical chemistry. If you search with the search engine of the term of the theoretical chemistry, so this is part of the learnings in the high school education. But what we are talking about is different from that. Currently, the chemistry is looking at the research on the molecule chemistry. And also, we know that the fundamental equations of physics as well. So those two are combined, and experiment would take place. So in that sense, we could say that this theoretical chemistry is a calculation chemistry. And this fundamental equation can be divided into two. One is dominating Newton equation for the classical mechanics, and also there is a Schrödinger equation for quantum mechanics. And in the area of the molecular dynamics, this Newton equation is often used. But this electron behavior-wise, the Schrödinger equation is used that look at the development of the time. But with that, the constant solution is given. And for that purpose, in this quantum chemistry calculation, time-independent Schrödinger equation is used. And for the molecular area, that is based upon the constant or the steady state. Therefore, this calculation is going to be very important. And of course, we have to do the challenge of the modern chemistry, especially energy and environmental issues. We want to come up with something new to solve such issues. And here it says, relatively strongly, it is some sets that it's a ridiculous method of reducing the CO2 emission to prevent the global warming. The chemists sometimes use such a strong words. What does this mean? For example, this photosynthetic reaction, if it becomes artificially feasible, then CO2, this is a material, so of CO2 would be required more. Well, that is actually what is happening in nature, and it's not something that a human cannot do that. And the source of that is the sunlight that is everywhere. Sorry, the order of the animation is opposite, but in 2010, Nobel laureates, Dr. Professor Negishi came up with these expressions. These are something that most of the chemists have in their minds. This is not limited to photosynthetic reaction. If this is possible and this is realized, energy issue and environmental issues can be drastically solved or changed, and there are many such possibilities. For example, hydrogen generation, hydration, and also the carbon dioxide fixation, methane conversion to alcohol, and also nitrogen conversion. If we want to do that, this is quite difficult to be done. And what you find at the bottom, that is a nitrogen conversion. There is the industrial method, but that energy loss is quite high, and that is not friendly to the earth. Against this, those with a less energy loss and possible to realize this reduction, if that kind of thing is available, we can get the benefit. So this is one of the challenges or the responsibility of chemistry. This is seemingly simple, but at the same time very important. But at the same time, it's very difficult to realize this. So what should we do? How can we realize this? Well, the nature knows all of this, so we can learn out of that. So where this is happening and the behavior itself is known thanks to the development of the scientific technology. For example, there is a protein, and there's a metal enzyme, and there's a reaction center. And there are complex molecule taking place. And looking at the atom, nickel, iron, mangan, and zinc, molybdenum, copper, such kind of a metal atom are always existing. So it is clear that these are impacting something here. But experimental-wise, how electron would be changed, that's important. However, it's very difficult to look at that level. So we have to introduce the theory. What is the structure of an electron? How electron is contributing to the reaction? That is necessary to be studied. However, unfortunately, with the current level of the quantum chemistry technology level, we cannot solve that. Why it's so difficult? Well, it is abnormal if there are the problems that can be easily solved. So there's exponential difficulty or complexity is here for the quantum computer. Rather, this cannot be handled with a classic computer. So there are 9 particles for the wave function, and here you have the volume and also the position. So you do the calculation here with the 2 times of such and such, and with this position, what will be the probability? So this is a distribution of probability. So all the combination will be necessary. And so even this model is simple, there are more than 100 million weights. So we cannot handle this large number. That's a difficulty. But what can we do with the quantum chemistry with this? There's some way. The previous grid type is very difficult, but we can think about the molecule trajectory that is introduced, and more than 90% is explained with this already fixed trajectory. And most of the molecules are in this way. Here you can find the water example. If it is a simple compound, well, in the case, the problem can be solved with a classical computer. What is difficult with this kind of introduction of the molecule trajectory? There are distribution and dispersion. So it ends up with the issue of a complicated combination. That's why we can introduce the quantum computing here. So the previous reaction can be assisted with the metal complex, and the center of the reaction well observed with that. And if the quantum computing is possible, completed, and we can use it easily, then such kind of problems can be dealt with. But what has been our approach so far? For many decades for this issue, we have been working very hard. And recent progress is the tensor network wave function usage. With that, the size of the issue that can be handled is bigger. The main research for that is something like this, and one of outcome of that is this is the calculation of the structure of electrons in an oxygen evolving center of photosynthesis. So we can go a bit beyond the limit with the introduction of this mathematical approach. However, if we want to know it in a more qualitative, quantitative manner, this tensor network is not sufficient. However, with this quantum technology, we can expand the limit, and if that becomes possible, we can contribute greatly to the modern science. That's something I am expecting. From here, let me change gear a bit. In order to get the expected outcome, what would be the quantum algorithm for quantum chemistry? Let me introduce you what we are doing currently. For example, there are many electron configurations, which is quite hard. This is a case of a classic computer. But with a quantum computer, it is clear that we can solve it. That's because, as you see, this electron configuration, look at the 0, 1, then with a 0, 1, 0, 1, with the direct closed space can be created. For example, there's a 50 qubit, and 2 times of the 50, in other words, 9,000 terabyte of the information can be obtained. And also you have to have the solution, how it can be prepared. That is the important thing. And from that solution, what kind of information can be extracted? These two are quite critical. But for that, different algorithms are developed. One important thing is an phase estimation or variational quantum Eigensteiger. So those are what we are also studying. And today I would like to focus on this VQE. I'm sure that you know VQE, you have heard it quite frequently. Therefore, I would like to skip it. So there's one initial state generated, and against that unitary rotation is applied, and the solution is approximated. And this variational quantum eigensolver, the approximate solution is not lower. If the energy is lower, meaning that the approximate solution is better. I don't know if that is right, but that is the approach we are taking. So this unitary rotation, how lightly we can apply that is quite important so that we can come to the true solution. And this Hamiltonian energy, how we can come up with it is another important thing. That we are not really satisfied with it. That's because we learned that the quantum computer really solved this in an accurate manner. But with this unitary rotation does not include the true solution. To what extent, no matter how extent you do that, what you can get is approximate. So next thing you can do is the designing of a unitary rotation. Depending on that expression capability, you can tell if it is successful or not. And the level of the success, even if the success will be decided. Of course, there's another reason for VQE collecting attention. Compared to other algorithms, the circuit tends to be shorter. Just one step might be sufficient for the time promotion. That is something that we can expect. So unitary rotation, how we can design, we are approaching for that as well. And what is demanded? First of all, physics-oriented. Based upon a physical model, unitary rotation is expected. And the other one is a trotter decomposition, as has been presented in the previous presenter. So trotter expansion, trotter free ansatz, and also the shorter circuit and higher accuracy. For this, what is quite a famous one is unitary coupled cluster ansatz. This is based upon the physics, that is fine. And but this is not trotter free. Therefore, a lot of trotter decomposition has to be applied. And if it is shortened, the circuit order will be impactful. And also this is quite deep. And the other one is highly efficient. This is not based upon physics, but this is friendly to hardware. Therefore, circuit can be shorter and jotter free because that concept cannot be applied. It has nothing to do with it. And what we're doing is to satisfy for these two. We would like to look for ansatz and a shorter circuit satisfying these two. And what we've developed ultimately is this one. There are different names considered, but the name given is the unitary cluster gestural ansatz. I'm not going to go into the details, but what is most important here is that with this, you can general chemistry, chemistry amplitude is utilized, and the roll rank approximation is applied here. What's good about this is that all the n depth and shorter, and this is physics oriented. So when we map up the chemical situation, then we can get the solution out of this. So this can be well applied. However, N2, that is a benchmarking molecule, and that's not what we are quite interested in. It has to be bigger. Therefore, going back to the beginning. So this is where that definitely the quantum chemistry is necessary. So there has to be the demarcation between quantum and classic, and between these two, there should be the electron correlation that has to be established. For this, first of all, the importance, just a simple separation. For example, chromium dimer, potential energy level cannot be well described, just like the case of blue. But looking at the interspace correlation, and for the first time, you can draw in a very clear manner for the bond energy. And for example, organic semiconductor, if that is looked in the excited states, you have to have that interspace correlation. Then, without that, order cannot be realized. With having this interspace correlation, for the first time, you can realize that this reproduction of the order and also the clear expression of excitation energy. So the combination is needed to be considered. There are two ways. One is using the classical solvers, and the other one is using the quantum solver based upon classical solvers. So, and vice versa. That's what we both are trying in our lab. And what I would like to introduce you is from quantum to classical. So the solution from the quantum solver get into the classical computer with extracting information, but that is costly. So that's the disadvantage of the first approach. We want to do the bigger molecules, so this one is one of them. The left one, this is a protein as a whole, but this orange and red and blue, this size of the molecule is what we are doing. This is a dicouple complex. For example, metal conversion, and that is where this dicouple complex plays a role. And for this, there are two stable structures available, and you have to have the inter-electron core relation between these two. Otherwise, you cannot come up with the structure you see on the left. With having that kind of a correlation, interspace coordination, the stable structure can be realized, and which is deeper type of the discussion can be possible. 600 qubit will be necessary, but it is now 12 bits, and the remaining is done by classical computer. So this is quite good. If you have around 59 bits, then yellow line, the most accurate result will be available. It seems time's up for me, but anyhow, we are trying to do this on the actual equipment, and we are working for the measurement cost. 1 unit, 100,000 shots. With that, we cannot get a significant result. So we are aiming at currently the 1 million. 10 to the power of 6 level of the shot will be necessary, which looks sounds quite difficult. But we want to work for that. So against the Hamiltonian tensor composition is introduced and make it as the terms to the simultaneous observation. But rather, one step beyond, we reduce the number of the shot for the measurement, and we want to do further calculation. Sorry about the time, but with this, I would like to close my presentation.